In the previous two lectures, we talked about electromagnetic waves that come naturally out of Maxwell's equations. In particular, we focused on wave propagating in the x direction and wrote this as E x t is equal to E 0 sine of k x minus omega t and B x t is equal to B 0 sine of k x minus omega t. If we generalize this, I can in general write for a wave propagating in the direction of unit vector n, I can write E r vector t is equal to E 0 sine or cosine or some other phase. So, I can write this as in general k dot r minus omega t and B as a function of r and t as equal to B 0 sine of k dot r minus omega t. And if I want to be even more general, I will add a phase also, some phase phi that can make it cosine or whatever, where the vector k is equal to 2 pi over lambda in the direction of propagation. In the previous lecture, we saw the waves were propagating in I direction, I dot E 0 was 0, I dot B 0 was 0. In the same manner, in general, I am going to have k dot E 0 is equal to 0. That means, the electric field is perpendicular to the direction of propagation, and similarly k dot B is going to be 0 and E cross B is going to be in the direction of propagation. With this background, what we want to focus on is again the waves of this kind, which are harmonic and plane waves. So, plane waves and harmonic or monochromatic or moving with frequency omega waves, and see what is the energy content of these waves, how much energy do they carry, in these waves, and how much momentum flow or how much momentum do they contain. Remember, these are the quantities we had already calculated for electrostatic field. What we are going to also focus on, that omega is going to be large. So, we are talking about something like the 10 raised to 15, 10 raised to 10, 10 raised to 14. That means, in 1 second there are so many oscillations. We are talking about light waves or microwaves. In that case, it does not make sense of energy variation, but we will be talking about time averaged energy. And what we mean by this, we will be taking 1 over the time period and integrate whatever quantity we get from 0 to t over time, whatever quantity, energy density or the energy flow or momentum flow. So, at such high frequencies, what we see, for example, if I am looking at this light, I am not seeing it varying, I am seeing a constant light, because it varies 10 raised to 15 times per second, and therefore, I see only the average light, my eye somehow averages out. So, we have E equal to E 0 sine k dot r minus omega t and B is equal to B 0 sine of k dot r minus omega t. If you want, you can add a phi also, but does not really make a difference. Let us calculate the energy first, energy content. Recall that energy in the electric field is 1/2 epsilon 0 E square, and therefore, in this case this is going to become 1/2 epsilon 0 E 0 square, that is the amplitude square, sine square k dot r minus omega t. Recall I said that this is varying in time very fast. So, I will be talking about average energy. average energy is going to be 1 half epsilon 0 E 0 square 0 to t 1 over t sin square k dot r at a given point, r is fixed, minus omega t dt. And this you know from your ordinary mathematics is 1 half. So, this becomes 1/4 of epsilon 0 E 0 square. Let us now calculate what the energy in the magnetic field is. Magnetic field, you recall, is carries energy 1 over 2 mu 0 B square, which is going to become 1 over 2 mu 0 B 0 square sin square k dot r minus omega t, which when time averaged will give me another factor of 2. So, this becomes 1 over 4 mu 0 B 0 square. Recall from previous lecture that B 0 is nothing but E 0 over C. So, this becomes 1 over 4 mu 0 E 0 square over C square, but 1 over C square is mu 0 epsilon 0. So, this becomes 1/4 epsilon 0 E 0 square. Therefore, the energy content in the electric field and the magnetic field component of this electromagnetic wave is exactly the same, which is 1/4 epsilon 0 E 0 square, and you add the two and you get the energy density in an electromagnetic EM wave to be 1/2 epsilon 0 E 0 square. So, when this wave exists, for example, this light is coming to me, then in between average energy per unit volume is 1/2 epsilon 0 E 0 square. So, this wave, let us again take it as if it is propagating in x direction. If I take a small box here of unit volume or small volume dV, then energy content in this is going to be 1/2 epsilon 0 E 0 square dV. How about the energy flow, which is related to intensity, which is related to Poynting vector. The Poynting vector is given as 1 over mu 0 E cross B, and we have already seen that E cross B is in the direction of propagation. So, I can write this as 1 over mu 0 direction n mod E 0 and modulus of B 0 sin square k dot r minus omega t. B 0 we recall that is again E 0 by C. So, I can write this as 1 over mu 0 in the direction of propagation E 0 square over C sin square k dot r minus omega t. When I take the time average, sin square k dot r minus omega t is going to give me a factor of 2, 1/2, and therefore, this becomes 1/2 E 0 square over mu 0, and C is nothing but square root of epsilon 0 mu 0 1 over. So, this becomes 1/2 square root of epsilon 0 over mu 0 E 0 square in the direction of propagation. That means, if there is an electromagnetic plane electromagnetic wave going in some direction, in the same direction per unit area per unit time, the energy that flows is 1/2 square root of epsilon 0 over mu 0 E 0 square. Let us also see it from the energy density point of view. The energy flow, if you recall from one of the previous lectures, is going to be nothing but C times the energy density U, which is going to be 1 over square root of epsilon 0 mu 0 times 1/2 epsilon 0 E 0 square, which is same as 1/2 square root of epsilon 0 over mu 0 E 0 square, same answer. So, that is the energy that is carried by the electromagnetic wave, or that is the intensity that we receive. This is also related to the momentum carried by electromagnetic waves. Recall that the momentum density is nothing but S over c square. Let us check that. Modulus of S, this is nothing but energy ml square t minus 2 per unit area per unit time, which then becomes equal to momentum density is ml t minus 1 over L cubed. So, if I divide by c square here, c square is nothing but L square t minus 2, this cancels. So, I am doing c square. One of the L's I can cancel and make it L. So, I get m L t minus 1 over L cubed. So, this is the momentum density, and therefore, if there is a plane electromagnetic wave going, the momentum density is given as 1/2 square root of epsilon 0 over mu 0 E 0 square over c square. Given this momentum density, what is the momentum flow? The momentum flow is nothing but c times the momentum density, which is going to be equal to 1/2 epsilon 0 over mu 0 E 0 square over c. Let us rewrite them in terms of u. So, S is nothing but c times u, u is the energy density in the electromagnetic field over c square, which is u over c, and the momentum flow is nothing but u itself. If there is momentum flow, that means if there is an electromagnetic wave going this way, it carries a momentum which is equal to u per unit area per unit time. What does that momentum do? Suppose I put a screen here which absorbs all this radiation falling. If all the radiation falling is absorbed, that means all the momentum u per unit area per unit time which is coming gets absorbed in this. So, this screen should get a momentum in this direction, which is momentum per unit time per unit area is nothing but force per unit area, which is equal to pressure. So, an electromagnetic wave falling on a screen where it gets absorbed applies a pressure equal to its energy density. If the wave reflected perfectly, then the momentum coming in per unit area per unit time would be u, momentum going out would be u again, and the pressure would be equal to 2u. So, I conclude this lecture by restating again that EM waves carry energy, which we see in the form of light or heat, which comes to us from the sun. EM waves carry momentum, and this implies they can apply pressure on the surface on which they